All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good, good. Everyone keeping cool. It's got really, really hot all of a sudden. Like really hot. We're like it's almost like we're in July right now. Okay. All right. So plan for today is we're going to continue our lecture notes from last Thursday. So last Thursday we introduced this idea of the strong and weak form of boundary value problems, and so we finished going over the strong form. So we are going to go over the weak form today, and we're going to talk about why that's useful for finite elements. So again, we're not going to talk about any finite elements today. We're kind of more just setting up our discussion for the next class. Okay. All right. So announcement. So I'm still working on grading your guys' midterm exams, and so I'd say I'm about halfway done. So I should definitely have them ready by Thursday. So if you want to come to class on Thursday to pick them up, they will be ready for you at that time. And so yeah, so I think yeah, definitely they'll be ready by Thursday for you to pick up. So I think I should be done by tomorrow night, and so the grade should be in Canvas by tomorrow night, and then Thursday you guys can pick them up in class. Okay. All right, any questions I can answer before we get started for today? Okay. Okay, all right, so let's go ahead and get started. Okay, so when we last met, we were talking about this idea of the weak form of a boundary value problem. Okay? So, last time we were in class, we went over the definition of a boundary value problem. Those are problems that you've likely seen before in your previous classes. So remember, for a boundary value problem, okay, and so I'm kind of shortening it to BVP so the boundary value problem is long to say. There's essentially three components, right? So on the one hand, we have our geometry, okay? Or another way you can say is that we have our domain, okay? So that's going to be the region on which we want to solve our problem on, okay? So in general finite elements, your domain is usually going to be a three-dimensional domain, sometimes a two-dimensional domain. So that's obviously going to be defined by your CAD geometry if you're talking about using ANSYS. But in one dimension, in 1D, usually your domain is going to be a lower bound for x and an upper bound for x. Okay. So in 1D, this is going to be maybe x1, which is less than or equal to x, which is less than or equal to x2. Okay. So there's a lower bound and an upper bound. That defines our domain. Okay. Number two. So the next ingredient to a boundary value problem is your governing equation. Okay. So that is always going to be some kind of differential equation for our purposes. Okay. Specifically for our purposes, we're focusing on second order differential equations. Okay. So the highest order derivative that you will see in the equation is second order. Very specific, I know, but actually there's a lot of physical phenomenon that are governed by second order differential equations. So it actually is a good skill to know. Okay, we're starting with ordinary differential equations where there's only one, one independent variable, only x. But we are eventually going to be working on 2 dimensions as well. So we're looking at partial differential equations by the time we reach the end of the class. Okay. All right, and the third ingredient is the boundary conditions. Okay. So boundary conditions is a concept that you guys are very familiar with. We've dealt with them a lot in our direct stiffness methods, right? Essentially, the boundary conditions basically describe or they define, how your system is behaving at the extremities of the domain. Okay. So the important thing to remember with the boundary conditions is that they're always defined or always prescribed at the extremities of the domain. Okay. Which in 1D, we only have 2 extremities. So there's x1 and then there's x2. Okay. So you're usually going to have one boundary condition at x1 and another boundary condition at x2. Okay. And remember, there are 2 types of boundary conditions that you can have. You can either have Dirichlet boundary conditions, or you can have Neumann boundary conditions. Okay. Okay. So with all this in mind, we presented what's called the strong form. Okay. All right. So I'm just going to review that very quickly. Okay. So the strong form of a boundary value problem is typically what you've kind of seen is just basically all 3 of these ingredients, just all kind of listed separately. Okay. So for instance, your domain is, let's say that we have 4x, or let's say x1 is less than or equal to x, let's say equal to x2, okay? We have our differential equation, which is d dx of e times a d u dx, okay, plus b of x is equal to 0, okay? Right, so that's our domain, that's our differential equation, right? Second order differential equation, if you kind of distribute the d dx throughout the entire equation there, okay? And then we have our boundary conditions. So let's say that u of x1 is equal to u naught, and then let's say that du dx at x is equal to x2 is equal to some some Neumann boundary condition. Okay, so the strong form essentially takes all 3 components of the boundary value problem and just kind of lists them separately. Okay, and then to solve this equation, typically you would first work off the differential equation and then solve for a solution for that. Okay. Okay. So to solve the strong form, you first solve a general solution for the differential equation. Okay. Right, so that's kind of traditionally how you learn how to solve differential equations back from your math class or your engineering analysis class. Okay, then you would use the boundary conditions to solve or to compute the arbitrary constants in your solution. Okay, so this is a very kind of traditional way to solve differential equations with boundary conditions. Okay, so we call that the strong form. Right, so last time when we were here, we kind of derived the strong form for 1D elastodynamics, or elastomechanics, excuse me, not doing dynamics just yet. And we did an example. Okay. Now the weak form is going to have all 3 of these components, but it's going to formulate them in a different way to allow us to do a different kind of solution procedure. Okay, so that's kind of where I want to end up today. So where I want to end today is talking about how we can solve for approximate solutions to the weak form. Okay, but that's where we need to kind of work up to. But that's kind of where we kind of ended last time. So we introduced this idea of the boundary value problem. We kind of talked about its strong form, and we kind of just summarized very quickly how to solve for its solution to the strong form. Okay. Okay. Any questions on that? That's just a kind of a summary from last time. Okay. All right. So let's talk about weak form. Okay. Now, the weak form, we'll kind of talk about in a bit why it gets the name weak form. But remember, weak does not imply worse, right? So there's nothing wrong with the weak form. It's not any worse or better than the strong form. In fact, you can take the word form kind of literally. It's just a different form of the same problem. So it's literally the same problem. We're just expressing it in a different way. Okay, so the first thing we're going to talk about today is, how do we obtain the weak form from the strong form? So I know we kind of started that discussion last time, but it's kind of been a long weekend. It's been really hot outside, so let's just kind of go from scratch. Okay. Okay. So how do we get the weak form? So the first step, right? So typically to derive the weak form, a lot of times we start from the strong form of the problem. We start from the boundary value problem, and we kind of derive it from there. Okay? So starting from the differential equation, okay, so let's write that first. So let's write d dx of EA du dx plus b of x is equal to 0. Okay. Right. And so what we're going to do is we're going to take this entire expression here and we're going to multiply it by what's called a weighting function. Okay. So we're going to take this entire expression, we're going to put parentheses around the whole thing, and we're going to multiply it by some w of x. Okay. Okay, where w of x, for now, you can think of it as just like it's just an arbitrary function at this point, okay? But we are going to place some restrictions and some requirements on w of x, okay? All right, so this is an arbitrary, so for now, it's just an arbitrary function. You'll see kind of later what this function is for, okay? We are going to require, okay? So even though w of x is an arbitrary function, it's essentially, we're going to treat it as if it were kind of like a solution, right? So it's almost like a parallel, kind of like the weird twin cousin of our solution variable u, okay? So a lot of the behavior of w is actually going to mimic the behavior of u, right? So one of the requirements that we're going to have is that whenever u has a Dirichlet boundary condition, we're going to require that w of x specifically goes to 0 at the location of the Dirichlet boundary conditions. All right, so remember, a Dirichlet boundary condition is a boundary condition where we're directly specifying the value of u. Okay, so if we go back to our boundary value problem that we defined earlier, right? We have our two boundary conditions here. This one right here, we're directly specifying the value of u. This one right here is our Dirichlet condition. Okay. So whenever we have a situation where we're directly saying that u at this location or u at this boundary is equal to some value, now that value may be non-zero, right? It doesn't necessarily have to be a non-zero value. In fact, we have that here, right? But whenever we have a Dirichlet boundary condition, w of x must equal to 0 at this location. Okay. Right. So for this particular example, okay, right, we can say that w of x1 is equal to 0 since u at x1 is equal to u naught. Okay. Okay. So that's w. So that's the only requirement we're placing on w. So w from there can kind of be whatever it wants to be. Okay. Right. Eventually, we are going to place some more restrictions on w. Kind of closely aligned to what we're going to require for u as well. But for now, that's the only thing. Okay. Okay. And so the next step, which is this is kind of where a lot of the magic happens, is we're going to take this expression. Well, first of all, we can distribute w throughout the whole thing. Okay. Let's do that first, actually. So let's distribute w of x. Okay. So there's only two terms here. So we have the derivative term and we have the source term. So we have, kind of block this off just so it's a little easier to see. Okay. So we have w of x multiplied by d dx of e times a du dx plus w of x b of x is equal to 0. Okay, so we have two different terms here. So we have the derivative term with w of x and we have the source term with w of x. Okay. Now, what we're going to do with this expression here is that we're going to integrate this entire expression across our entire domain. So we're essentially integrating from x1 to x2 because that's the length of our domain, right? So we're going to integral from x1 to x2 of w of x d dx of ea du dx dx plus integral from x1 to x2 of w of x b of x dx is equal to 0. Okay. Okay. So we're going to pause here for a second because there's quite a few things that kind of happen at this stage right here, and quite a few things that we can actually accomplish and kind of explain. But that's the idea of the weak form, is to take your differential equation and essentially get it into a form where you can integrate across the entire domain. Okay. Any questions on anything that we've covered up to this point? Okay. All right. So let's kind of pause here and kind of see what we have at first, right? So we have an integral of our equation across the entire domain, right? And so this is kind of where the difference in definition kind of becomes clear, right? And so in the strong form, the strong form kind of gets its name because, by solving the differential equation by itself, we are basically enforcing the equality, we're enforcing our equation at every single point within the domain. Whereas the weak form we're no longer caring about what things are happening point to point, right? Because we're integrating across the entire domain. And so we can say that our equation now is enforced in total across our entire domain through the integration. Okay. So the end result is the same, right? So in the end result, you're solving your equation throughout the entire domain. It's just that the way you accomplish that is a little bit different. Where strong form, you can think about going point by point and make sure your equation is enforced in that sense. But for the weak form, we're essentially kind of solving for the entire equation throughout the entire domain at once through the integration operation. Okay. Right. So mathematically, we say that strong form provides a strong enforcement of the equation because it's point by point, whereas weak form, we're weakly kind of enforcing the equation across the entire domain, but the end result is exactly the same. So you still get the same result. It's just the way that you accomplish it, the way you interpret it is just a little bit different. Okay. Okay. All right. So that's one thing to note here. So that's one thing we get from the integration. The other thing that we get to do is we get to play around with the integrals with our integration rules a little bit. Okay. In particular, right? So I think this is kind of the last point that I made on Thursday, right? We have this expression here, right? We have a situation where we have kind of an imbalance of derivatives. Right? We have our solution function u, which essentially has two derivatives on it, right? So it's a d dx and a du dx. And our w here, which only has zero derivatives on it. And so it's just w of x by itself, okay? Right? So what we can do is that, because we have these expressions in integral now, we can kind of balance the derivatives through integration by parts. Okay, so if you remember, the way we do integration by parts, so we have a u, we have a dv, okay? So for u here, we're going to set it equal to w of x, right? For the dv part, that's the part we're going to take the antiderivative of. We're going to have d dx of ea du dx, okay? Dx as well, I believe. Okay. Okay. All right, so for the u part, we're going to take its derivative. So we have du is equal to dw dx. And then for the v part, we're going to take the antiderivative. So the antiderivative is going to cancel out with one of the derivatives there. And so we end up with ea du dx. Okay. And there's a dx for the du as well. Okay. And so in traditional kind of integration by parts, we're going to go diagonally down first, right? So we're going to take u times v, and so we're going to take the product of w of x and ea of du dx minus integral of the product of v du. Okay. Okay, and so we do that. What we get is, so we started with integral of x from x1 to x2 of w of x d dx of ea du dx dx. Okay, right. So we apply integration by parts, and then what we get from this is product of w times e times a du dx. Okay. That term there is fully integrated, so we're going to evaluate this at our integration bound. So this gets evaluated at x1, x2. Okay. So that term does not need any more integration. We've already integrated it. Okay. Minus integral from x1 to x2, okay, of du times v. So we have dw dx times e times a du dx dx. Okay. Okay. So by performing integration by parts, we get two very interesting terms here, two very interesting expressions, okay? And you're going to see that it all kind of comes back to our boundary value problem definition, okay? All right, but before we do that, any questions on how we got to this point here? Okay, okay, good. All right, so first thing that we have here is we have, let's look at this term right here, okay? So that expression right there, we can see that we've already performed the integral. And so essentially when we evaluate this at the integration bounds, right? We're essentially going to get an expression that only takes place at the boundaries, okay? Okay, so eventually what we get here is we get quantity W times E times A du dx at x is equal to x2 minus same quantity W times EA times du dx evaluated at x is equal to x1, okay? All right. And then our second derivative is, our second integral there is still going to be the same. So we're going to take a minus integral from x1 to x2 dw dx times e times a du dx dx. Okay. Okay. All right. So let's take a look at the terms in pink first, because those ones are going to be interesting. Okay. In particular, let's look at this one right here. Okay. Okay. So we have the quantity w times e times a times du dx evaluated at x is equal to x1. Okay. Now, what did we say about W before we began all of this mess here, right? So we're going to scroll up here, right? So since for this problem, right, we have a Dirichlet boundary condition at x is equal to 1, right, or x is equal to x1, that means our W function is going to be 0 at that location, okay? Now let's come back down here, right? And so we can see that we're evaluating this expression here, W times E times A times du dx at x is equal to x1, okay? So since for this problem, U has a Dirichlet boundary condition at x is equal to x1. Okay. That means that W of x1 is equal to 0. Okay. And so that means that this entire expression here, since W is equal to 0, right? 0 times E times A, doesn't matter what E times A are. You know, I mean, technically you have a singularity if they equal to infinity, but that's not possible. Okay. So this entire term here is going to go away because of the requirements on our weighting function. Okay. All right. Then the other thing that we have here is, right? So this other expression here, right? This W times E times A times du dx at x is equal to x2. This is where we have our Neumann condition. So remember, for this problem, we have du dx at x is equal to x2 is equal to gamma naught. Okay. right? So we can go ahead and plug that in. So we have, for this expression, that we have w at x2 times e times a times gamma no, okay? Minus, we still have our integral from before. So we have minus integral from x1 to x2 times dw dx times e times a du dx dx. Okay. All right, and then last thing that we need here is a term that we almost forgot, right? So we go back to our original integral, right? We've only just been working on just that first integral there in pink. We also have this integral of the source term as well, right? So it's integral from x1, x2, w of x, b of x, dx, okay? We didn't do anything with it just because there's not really much we can do because we don't know what b of x is. But let's go ahead and add it back in here. So we have plus integral from x1 to x2, w of x, b of x, dx is equal to 0. All right, so what we have here is essentially, this is the weak form of this problem. Okay, good. All right, so this is for a specific boundary value problem, right? And so, I did try to be as general as I could, but this one does require that you have one Dirichlet boundary condition, one Neumann boundary condition. So, just like our direct stiffness method, the important thing with this kind of derivation here is the process. Because if you had a different boundary value problem here, so you had different boundary conditions, you need to know kind of how to adapt, okay? And where that kind of mostly changes here is in kind of the application of this step right here, which is essentially going to be your application of the boundary conditions. Okay. Okay, but so I just wanted to make sure that that part is known right there. Okay. Okay. All right. So now that we have this weak form, let's talk about some interesting features of this weak form that we can make use of. Okay. All right. So the first thing that we notice, right, is that because of our integration, right, we get kind of one expression here, one equation that incorporates both our governing equation and our boundary conditions together into the same equation. I guess specifically the Neumann boundary conditions are now incorporated directly into our equation. Okay. Whereas if you look at our strong form, our Neumann boundary condition kind of was on its own, and it was applied alongside our Dirichlet boundary condition. Okay. But because of the integration by parts, we can now incorporate the Neumann boundary condition directly into our equation, which is actually pretty huge. So that does help us with finite elements. You'll see probably sometime next week. Okay. Okay. The other thing to note here is that our derivative, we've kind of softened the harshness of the derivative through our integration by parts, okay? Now our highest order derivative that we have here is only first order. Okay? Right, so we've basically taken one of the derivatives off of our solution variable u and then place it on our weighting function instead. And so that fact actually helps us out pretty tremendously, okay? Because now what we can do is we can now assume certain forms of our solution and get something without too much trouble. Okay, so those are kind of the two main benefits that we receive from getting this weak form. Is that on the one hand, our Neumann boundary conditions are directly input into the equation, so that's kind of one less step that we have to do later on. But more importantly, we were able to balance and kind of soften the order of the derivatives. So now, it's not strictly a first order differential equation because we do have the product of derivatives, but the highest derivative that we do have is only first order, right? And that does actually help us out quite a bit. Okay. All right. Any questions on this? Okay. All right. So then the next thing that I want to kind of do is kind of focus on solutions to these to this problem here. Okay. But before I do that, let's kind of take the same methodology and apply it to heat transfer as well. Okay. So actually, one kind of big shift that we're going to get in the that we're going to see in the second half of the class is we're going to shift away from kind of structural mechanics, structural equations, and we're instead going to talk about the heat equation instead. Okay. Now, in one dimension, the heat equation mathematically is exactly the same as a structural equation. Okay. Okay. So the only thing that changes is just the symbols for the variables, right? And so what we have instead of E and A, we have K and A instead. And instead of our solution variable being U, the displacement, we now have T for the temperature. Okay. So the 1D heat equation is given by the following. So you have d dx of K times A of dt dx, okay, plus S of X is equal to 0. Okay. So that's kind of the strong form of our equation there. Okay. All right. Where K here is a material property of our domain. So this here is the thermal conductivity. Right. So you don't necessarily have to know what the thermal conductivity is. This is not a heat transfer class, but for our purposes, you can assume that it's strictly just a material property of the material in the exact same way that Young's modulus is. Okay. All right. A here actually has the same definition. So A here is the cross-sectional area. Okay. Right. So heat transfer also depends on the geometry of the material. Okay. T here is the temperature. And S of X here, this is what's called the internal heating of the material. Right. So the internal heating kind of has the same role as the body force. It's just an additional function that you can add to your function or to your differential equation that that kind of models some kind of internal heating in the material. Okay, so in 1D, it's exactly the same. So, I don't want to spend too much time kind of dwelling on this just because it's mathematically it's exactly the same. But I will note that in 2D, okay, and 3D, I suppose, as well, but we're not going to do anything in 3D in this class. Okay. In 2D and 3D, the heat equation actually becomes simpler to solve because the heat equation is still a scalar equation. And what that means essentially is that the unknown that we're solving for, which is temperature, is a scalar quantity, right? And so you contrast that with elasticity, right? So in 2D and 3D, elasticity, right, where we're solving for structural displacement, structural stresses, things like that, elasticity actually becomes a vector equation. And so not only do you have to solve for the displacement, but you have to solve for the displacement in the x direction, displacement in the y direction, and in 3D in the z direction as well. Okay, so it does actually complicate things quite a bit. Not that it's impossible, it's definitely possible to solve vector equations. That's obviously that's why ANSYS exists, but it's just the math just becomes a little bit too cumbersome. It kind of detracts away, I think, from the purpose of FEA. So once we get to 2D and 3D stuff, we're basically working exclusively with the heat equation. Your final project is going to be on the heat equation as well. And so, I wanted to introduce it. But mathematically, it kind of works exactly the same. Okay. So we can take this equation, we can derive its weak form as well. Okay. And we can kind of solve it in the exact same way. Okay. Now, let's talk about, one thing we can do with weak forms that's, a little bit harder to do with strong forms. Okay. All right, so first let me note, we can derive weak form okay. All right, so you can go through the exact same process that we did earlier in class today, where you basically multiply by a weighting function, you integrate across the domain, and then you do integration by parts. You can get the weak form in the same way. Okay, so I'm not going to go through that, even though in the notes I do that. Okay. Now with the weak form, right? One thing that we can do that's really interesting is we can do what's called an approximate solution to our weak form equations. Okay. And so this part right here, this is kind of the segue into our finite element forms, right? Because we're essentially going to be doing the same thing with FEA forms. Okay. Okay. All right. So let me kind of start by saying that typically when you have a strong form equation, right? Typically you kind of solve for the solution without any assumption of what the solution may look like. Okay. So typically when finding okay. So when you're finding strong form solutions, you kind of just solve the problem. So you don't really stop and think, what if our solution looks like this, right? Right. So whatever the form may be, that's just the form of the solution. Okay. Now, this is great when it works, right? So when you're able to solve the equation and you're able to kind of solve it without any assumptions, that's generally the best thing that you can do, because then the solution just ends up being what it is. Okay. But, with FEA and with kind of 2D and 3D problems, usually we're not in a position to do this. Okay. And so that technique of kind of, just solving for the solution without any assumptions, we call that a direct solution. Okay. So we can't always solve directly because a lot of times, our situation, either our equation or our boundary conditions, our domain is very complicated. right? So let's say that, let's just even go just up one dimension, right? So let's say you have a 2D heat equation, right? The methods for solving partial differential equations are not easy to say the least. And so, I know a lot of you guys are all grad students, and so probably everyone here has taken 438 or 538, right? Or you're going to take it soon. And so what you've seen is that as soon as you have a partial differential equation, you know the training wheels go off. That's all that I'll say about that, right? And so kind of a direct solution is just not always possible. Okay. And that is doubly true for finite elements as well. But what you can do in situations like this is that you can solve for an approximate solution. Okay. And so what if you kind of solve for the solution kind of in a backwards way, where before you start, let's say that we're going to make an assumption in terms of what our solution is going to look like. Okay. Okay. So we're basically going to say that it's going to be impossible in some situations to solve for a direct solution. But what if we make an assumption of what our solution looks like? In other words, we kind of pre-assign a form of the solution. Okay. Because then what that allows us to do is that it allows us to plug in our assumption into our governing equation. Okay. All right, and then once you do that, then believe it or not, it actually becomes much easier to solve the equation because you already have an idea of what you want your solution to look like, right? Now that assumption may be correct, it may be incorrect, but at least you have a starting point, right? And that actually makes your solution procedure much easier to do. Okay? Now it's not going to seem easier in one dimension because in 1D you can just say I can just solve this directly, and that's often faster. But once we get to 2D and eventually 3D, right, then this method becomes necessary because you're not going to solve that partial differential equation. Okay. All right. So the idea is like this, and so let's say, okay, let's assume, right. So a very common assumption of form is that usually we assume that our solutions are polynomial in nature. Okay. So let's assume our solution is a quadratic polynomial. Right? And so that means, and that, I'm going to go based on the heat transfer one. So that means we're going to assume that T of X is equal to, right? So we don't know exactly what the coefficients of that quadratic polynomial are going to be, but we can at least create a generic quadratic polynomial, right? So we can say this is equal to A0 plus A1x plus A2x squared. Okay. Right. So we have the constant term, we have the linear term, and the quadratic terms all accounted for there. Okay. All right. So our goal is essentially that we're going to take this form, we're going to plug it into our weak form, and then solve for the values of A0, A1, A2 in order to get the best possible quadratic polynomial for our solution. Okay. Now, it could be, and in most cases, this is probably true, that our solution is not actually a quadratic polynomial. It probably has some other functional form, right? So we're not getting the exact solution here. We're getting an approximate solution, but we are going to get the best possible quadratic function that best mimics our solution. We're going to get it in a much, much easier way. Okay. Okay, so that's the idea. And so, for the rest of the class today, I do have, we're just going to work on just one example, right? So we're going to take a situation, we're going to solve for its solution in the strong form, and then we're going to solve for its solution in the weak form using this approximate kind of methodology. Any questions on this? Okay. Oh, I almost forgot. And it's fitting that we forget this just because people forget it all the time, right? We not only do we have to assume a form for the solution, but we also have to assume a form for our solution's weird twin cousin, the weighting function as well. So let's also assume. Okay. So one of the requirements for the weighting function, right, besides the Dirichlet boundary condition thing, is that our weighting function is also going to have the same functional form as our solution. Okay. Okay. And so because we are assuming t of x is a quadratic function, that means w of x is also going to be a quadratic function. Okay, so it's equal to b0 plus b1x plus b2x squared. Okay. Okay. So again, we have another set of unknown coefficients, b0, b1, b2. But you're going to see that the values of those coefficients actually don't matter, and so they're just going to be there to help facilitate our solution. But we actually don't really care what those are because we only really care about our solution. Okay. Okay. All right. So let's go ahead and work on an example. Okay. So this is going to be an example from heat transfer. So let's say that we have a rod that's subjected to some kind of uniform heating. Okay. Okay. All right. So let's say that we have a rod that's attached to a wall. Okay. I know it looks just like a beam, right? But we're looking at this from a heat transfer perspective. Okay. At the wall, we're going to say that we have a fixed, an assigned temperature. So T at the wall is equal to 25 degrees Celsius. Okay. So you can see we have a prescribed boundary condition there. We have a Dirichlet boundary condition at the wall. Okay. And at the other side, right, we're going to assume that we have an adiabatic tip. And so what that means is that we're going to have no heat flux at that tip. Okay. And so essentially that means that the derivative of our temperature is going to be 0. Okay. Okay, so the length of the fin, let's say it is 5 meters. It's a long-ass rod. I think it's just to make the numbers a little bit more convenient. Okay. And let's say that we have some kind of uniform heating. Okay. All right, so let's say that we have some kind of uniform heating that is occurring throughout the entire rod. Okay. And so we're going to model that uniform heating as our function s of x. Okay. And we're going to say it's going to ramp up as you get further down the rod. So we're going to say that s of x is equal to x squared divided by 5. Okay. Okay. Last thing we're going to need here is we do need the material properties of the rod. And so we're going to say that the thermal conductivity of the rod is 2 joules per meter degree C seconds. Okay. And the cross-sectional area, we're going to say is 0.5 meter squared. Okay. Just to make things simple and cancel it. Okay. Okay, so for this example, we're going to do two things. Okay. All right, so in both parts of this problem, we are going to solve for the temperature distribution T of x. Okay. Okay. So we're going to solve for a solution for T. Okay. And so the first method that we're going to use is we're going to solve the strong form and we're solve it directly. Okay. And part two, and so in part two, we're going to solve for an approximate solution to the weak form. And we're going to make an assumption of a quadratic solution. Okay. Okay, so that's the goal, right? So we're going to do part one, direct solution of strong form. We did that last time, so we're just going to go fairly quickly with that. And then part two is we're going to assume a form. We're going to assume a quadratic form for the solution and solve for its weak form from there. Okay. All right. Any questions on just the setup or the problem statements? Okay. All right. So let's go ahead and do our solution here. Okay. Okay. So part one, let's do the strong form first. Okay, so let's go ahead and plug in for our strong form. So we have d dx of k times a dt dx plus s of x is equal to 0. Okay. All right, so let's go ahead and plug in for all of our properties here. So k times a, right? Conveniently, k times a is going to equal to 1, right? And so first term here, we have d squared t dx squared plus s of x. So s of x in this case is x squared divided by 5. Okay. And all of this is equal to 0. Okay. All right, so we have a fairly simple case here. So we're just going to move the x squared divided by 5 to the other side of the equation. Right, so we have d squared t dx squared is equal to minus x squared over 5. Okay. All right, so we don't need to do any kind of special tricks here. We can just solve for this solution just by straight up integrating. All right, so in fact, we're going to integrate twice. Okay. All right, so we integrate twice. Each time we integrate, we have to add an arbitrary constant, right? And so we do that, we get t of x is equal to minus x to the fourth divided by 60. Let me clean that up a bit. Plus c1 times x plus c2. Okay. And this right here is our general solution. Okay. And so from here, we are going to basically apply our boundary conditions because we want to solve for C1, C2, right? All right, so our boundary conditions here is that we have our Dirichlet boundary condition at the wall, right? So we have t at x is equal to 0 is equal to 25, right? Because we're defining x is equal to 0 to be at the wall right here, and at the end we're gonna have x is equal to L. Okay. And so we plug in 25 for this, and so we get or plug in x equal to 0, excuse me. So you have minus 0 to the fourth divided by 60 plus C1 times 0 plus C2. Okay. So in this situation, this is, I think, our first time we have a Dirichlet boundary condition, which is non-zero, right? So that was a question on the exam. So this is one that, we're gonna have to be careful of once we get to finite elements, okay? And so we plug this in, we get C2 is equal to 25. Okay. And then our other boundary condition is dt dx at x is equal to 5 is equal to 0. Okay. All right. And so we go ahead and take the derivative. So we have dt dx is equal to minus x cubed divided by 15 plus c1 is equal to 0. Okay. Right, so we plug in x is equal to 5, we get minus 5 cubed divided by 15 plus c1 is equal to 0, right? We simplify that and we get c1 is equal to 25 over 3. Okay. All right, so now that we have C1, C2, we can go ahead and plug those in, and that gives us our final solution. Okay, so we get T of x is equal to, let's see, minus x to the fourth over 60 plus 25 over 3 times x plus 25. So in this case, because we have just a simple one-dimensional situation, we are able to solve the equation directly, right? And so because of that, we can say this is our exact solution. Okay. So we didn't make any assumptions on the form of the solution, or we didn't make any assumptions on simplifying things. This is just the solution to our problem. Okay. Okay. So we want to take the same problem and we want to find an approximate solution by making the assumption that we have a quadratic form. Okay, so let's go ahead and start that. I don't know if we'll finish it today, but we'll definitely start it. So we're going to look at approximate solution. Assuming quadratic form. Okay, so if we're going to assume a quadratic form, we're going to say that t of x is going to be some quadratic function. So it's equal to a0 plus a1 times x plus a2x squared. Okay, and that means w of x is going to have the exact same form, but with different coefficients. So that means w of x is going to be b0 plus b1 times x plus b2x squared. Okay. All right, so what we're going to do is we're going to take this. First of all, we're going to apply our Dirichlet boundary condition, and so you'll see that that actually helps us solve for one of the coefficients right away. Okay. But another thing that you're going to see here is that if you look at our exact solution, right, our exact solution has a fourth order polynomial term, x to the fourth, right? If we look at our approximate solution doesn't have x to the fourth anyway, okay? So we're right away, we're kind of conceding the fact that, for this particular problem, it's going to be impossible for our approximate solution to match the exact solution. Okay. Okay. Now, this is kind of a unique case where, we're solving both the strong and the weak form. And so normally you don't have this information, but I think it's important to kind of note that at this stage, right, where we know we're kind of in this unique position where we know our exact solution has an x to the fourth term, right? It's going to be impossible to replicate that just because we've already kind of conceded that we're only looking for a quadratic form. So whatever we get for our approximate solution is never going to be exactly the same as our exact one. But, we can see how close we can get with the quadratic function, okay? Okay. All right, so when you're solving for approximate solutions, the first step actually before you plug it into the weak form is to first apply the Dirichlet boundary conditions, okay? Okay. So you can see that, when we're doing weak form solutions, we're kind of going backwards in a sense where, we're starting with an assumption of the solution. We apply our boundary conditions first, and then we plug it into the differential equation. Whereas for the strong form, we go the opposite direction. So in the strong form, we start with the differential equation, we apply our boundary conditions, and then we get our solution from there, okay? The reason we're applying our Dirichlet boundary conditions is that, we already have a form of our solution, right? And so, we can already apply our Dirichlet boundary condition to our assumed form, and that's going to allow us to solve for, usually at least one of the coefficients. Okay. Okay, so for this problem, we have a Dirichlet boundary condition at x is equal to 0. So we have t at x is equal to 0 is equal to 25. Okay. Right. And so let's plug in x is equal to 0 into our assumed form. That's going to be a0 plus a1 times 0 plus a2 times 0 squared. Okay. All right. And so that gets rid of those two terms there because they're just multiplied by 0, right? And we get right away that a0 has to equal to 25. Okay. Right. We're going to do the same thing. We're going to do the same thing at our weighting function. Okay. So remember, the requirements for the weighting function is that the weighting function has to disappear at the location of the Dirichlet boundary condition. Okay. Okay. So weighting function w of x, right? So we're going to plug in x is equal to 0. Okay. But instead of setting it equal to 25, right, remember that our weighting function has to disappear at the Dirichlet boundary. So that means w at x is equal to 0 is going to equal to 0. Okay. Okay. All right, so let's go ahead and plug in our coefficients here. So we have b0 plus b1 times 0 plus b2 times 0 squared. Okay. Right, everything multiplied by 0 is still going to go away. right? And what we get from this is 0 is equal to B 0. Okay. All right. Any questions on kind of how we did that step there? Okay. All right. So we only have 5 minutes left, so I don't want to get into the weak form just yet. But before we go for today, I do want to kind of mention a couple wrinkles that can happen with this particular step, because I think this step can be a little bit confusing for people, right? Okay. So for this particular problem, in a 1D problem, typically you're going to have one Dirichlet boundary condition and one Neumann boundary condition. Okay. It's technically possible to have a solution or have a situation with two Dirichlet boundary conditions. Okay. Okay. And so, in fact, I think one of the problems on the next homework, not the activity you guys are working on, but the problem set that have to do with this, does have a problem like that. We have a problem with two Dirichlet boundary conditions. Okay, you're going to want to apply both before you plug into the weak form. Okay. So don't just apply one, you want to make sure you apply both, right? And so that goes for both the solution function and the weighting function at the same time, okay? So the result of this is that, for the most part, you're going to be doing quadratic functions just because that's the function that kind of works best with this, okay? The result of that is you're going to solve for the solution of two coefficients instead of just one. Okay. So, whenever you're looking at a problem, make note of the types of boundary conditions. And if you have two Dirichlet boundary conditions, make sure that you apply both before you plug into the weak form. Okay. Okay. Another note that I'll make here is that, sometimes you're not going to get an expression where you can solve for a coefficient explicitly. Okay. Okay. All right, so what do I mean by that? So for this particular example, we have a very simple case here where, we apply our boundary condition, we get an explicit solution. So we can say right away that A0 explicitly has to be 25, okay? So we solve for a solution to one of the coefficients just straight up, okay? Sometimes that's not going to be the case. And so, let's say, for instance, let's say that our Dirichlet boundary condition was instead on the opposite side of the domain. So we have t at x equal to L is, let's say that it's equal to 50, okay? So that's not for this problem, so don't apply that here. But then if you plug that into your assumed form, we have A0 plus A1 times L plus A2 times L squared. Okay. Right? So technically, this is an equation that we can use, right? But it's not an explicit expression for where you can kind of just say that A0 is equal to this number, okay? But what we can do is we can get a relationship between one of the coefficients and the others, okay? So I think the easiest one to solve for in this case is still A0. So we get A0 is equal to 50 minus A1 times L minus A2L squared, okay? So even though, this may not be as satisfying because, we don't get an exact number, we do have an expression where we can relate this coefficient to the others, okay? And so even though we don't have an explicit expression for it, we can essentially say that this coefficient is solved, okay? So we no longer have 3 coefficients to solve for, we just have 2, right? Because if we solve for the value for A1 and A2, then that gives us the value for A0 as well, okay? So sometimes you'll get a situation like this, and so don't panic, it's fine. Eventually you'll solve for it once you solve for the rest of the coefficients, okay? All right, any final questions on this before we wrap it up for today? Okay, all right, so that's all we got time for today. So on Thursday, we will finish up this example. We'll plug this into the weak form. We'll see how to solve for the other coefficients in our problem. Remember, I'll have your exams ready on Thursday as well. So if you want to come and pick it up, you make sure to come to class on Thursday. I'll also bring the exams next week too. So if you can't make it Thursday, I'm not going to throw it away. It's your exam. So, you can either come to office hours and pick it up, or I'll bring it to lecture next week as well for you to pick up as well. Okay. All right, so thank you guys for coming today. Hope you guys have a good rest of your evening. Stay cool, and I will see you guys on Thursday. Yeah. I think you should be able to rely pretty heavily on the frame code. So, you can definitely copy and paste a lot of that code in there. I mean, the structure is going to be exactly the same. So you're going to be basically, defining your, all your properties, and then do the normal stiffness matrix assembly. But, so to answer your question, you can copy and paste the entire frame code and then make modifications from it.
Oh, yeah. So there, you don't have to take out structure.
No, yeah. You don't have to come up with your own structure. And so in fact, the structure that I have there is already pretty good. So
okay.
Yeah.
Okay. All right. Thank you.
Yep.
Just a silly question.
Yeah.
So the KA became irrelevant just because of the values, because it's effectively just
Exactly.
Okay. Yeah. Good. Just make it sure. All right. Thank you.
Yeah.
See you, Professor.
See ya. Good night.